Guys, this is a way to remind yourself, learn for the first time, or just simply learn for a second time about moment of inertia, trying to calculate the moment of inertia for different shapes and try to figure out what the A value is. What's going to happen is, if you haven't done so, line your paper up. We're going to do 4 different situations. And on this left side, I'm going to teach you the 5 steps or so in order to figure it out. And these will be 3 distinct situations. To give you a sense of what I'm talking about, situation number 1 is we're going to have a cylinder, mass M, radius R, and you're going around the center. Looks like this. We're going to figure out its moment of inertia. The second case is a rod of length 2L, mass M, also around the center. Total length 2L. The third situation is a rod of a density 3x, length L, mass M, located around the left edge. So you can think of it as this way. It's not really actually going up, but the mass here is super light, in fact 0. The mass over here is super big, so we're going to rotate it around. In each of these situations, however, we have the same steps and same result. What we're going to do is use this equation on your formula sheet to find it out. And you see the big problem. Almost all of our work is going to be try to change dm into dr. So you could integrate it, because right now you can't integrate r squared to dm. We're changing the r, but the mass is also changing. So a big part of our doing is getting dm in terms of r, dr, that kind of stuff. So let's begin. Step 1. We need to get dm in terms of the density. So far we talked about 2 densities. Density for a 3-dimensional figure and for a 1-dimensional figure. So looking over here, I know since the density of this is constant, that if I change the mass, the volume changes proportionally. So dm is rho dv. This is density. Here, I know that the density is also directly relationed. So it's dm over dr. If I put a little chunk here, the mass is going to go up proportionally. So dm is rho dr. It doesn't matter if it's 2L, 10L, or whatever. If you change the radius by a certain fraction, the mass will also change by that same fraction. And finally here, I know that density is dm dr, but now I have a term for my density. 3x equals dm dr. So dm is 3x dr. dr and x. In this case, x is how far you are from this point, and that's what r is as well, because you're going from here. So I could say, in this case, dr and dx, as well as r and x, are interchangeable, because we're starting from one end and going out. That's not true here, because starting from the center, the maximum distance I can go is L. So L equals R up to this point, but the total length is not 2R. Step 2. We're now going to set up the calculus, and we're going to pick the correct bounds of integration. So over here, I could say moment of inertia is integral of r squared dm, which is rho dv. You can see I have a little more work to do, because r squared and dv are definitely not the same. I can't do a direct relationship. This is a radius, this is the volume. But the bounds are what I care about. I'm going from the center, where r equals 0, to the edge, where r equals big R. So it's kind of like I'm making a radius that starts off as 0 and keeps getting bigger and bigger and bigger. In this case, integral r squared dm, that's rho dr. I actually have 2 possible bounds. The first thing I could do since I'm starting in the middle, is I can go from this 0 point out to just L, and that covers this kind of area. And I can just multiply by 2, because that would give me the other side as well. Or I can think of it as going from here to negative L to positive L. So you could think of it as R becoming those values. Since it's symmetrical, it doesn't matter which one you choose. I'm figuring most of you want to go this way. You start at the 0 and you go out that way. Distance L is multiplied by 2. But think of it, both ways are definitely going to work. Here, however, R squared, dm is 3x dx. I'm going to once again say, because R and x are the same because I'm starting out here, that I can just replace it with x squared 3x dx. And what I'm going to do is I'm going to say I'm going from here to out here. I'm going from 0 to L. One note, going from 0 to 2L here means you start here and go out there. That'd be appropriate if the axis of rotation was the left edge, not the middle. It has occurred to me you can't actually see that, so I apologize. I'll make good for you. The third situation, third point. We need to put your term in terms of R, dr, that kind of stuff. So looking over here, dv is not the same as R, so I need to get dv in terms of dr. Well, I know the volume of a right cylinder is pi r squared h. You might say, Jock, I thought the R was capital R here. Yeah, that's for the full cylinder. But what I'm doing is I'm starting off small and making it bigger and bigger and bigger. You might think, why isn't h not changing? Well, first of all, h is parallel to the axis, so h has no role to play whatsoever in the moment of inertia. And I know that because dv is to be the derivative of this, which turns to r. That's to be equal to 2 pi rh dr. Hey, I now have dv in terms of dr. If I put this back in, I can now say 0 to r of r squared times density times dv, which is 2 pi another r h dr. I now have dr with these r's, so I'm good. Looking here, I don't have to do any of this kind of stuff because I have dr and r. And looking here, dx and x, I'm good as well. Step 4. Integrate it, and we're going to pull out constants. Okay, looking over here, the constants in this case are rho, 2 pi h. Oh, I'm being foolish. Rho, 2 pi h. Integral 0 to r. I'm left with r squared and r. That's r cubed dr. Integrate it. This becomes r to the 4th over 4. Plug in 0 to r. And I'm left with rho times 2 pi h times capital R to the 4th over 4. I'm looking okay now. This one. Pull out. Only constant is density, because density is a constant. 2 rho, 0 to L, r squared dr. Integral of r squared is r cubed over 3. 2 rho, L cubed over 3 is my moment of inertia. Over here. Pull out just the 3. 0 to L, x cubed dx. Integral of that is L to the 4th over 4. So now I'm messing with some weird stuff here. I thought moment of inertia was always AMR squared or AML squared, whatever. I don't see an M in any of these. So the fifth thing is you got to put in for M. Looking over here. The only thing that could possibly have M in it is density. And since we're looking at R, the density now is the total mass over the total volume. Well, total mass is M. Total volume of a cylinder, we said before, was pi capital R squared H. Capital R because now we're at the biggest value. I'm going to put this in for that. And I get M over pi capital R squared H times 2 pi H R to the fourth over 4. And a lot of things are canceling out. The pi's go. R squared, at least R squared, which is great. The H's cancel. And a 2 and a 4 partially cancel. Onto the 1/2 mR squared, which is 100% the moment of inertia of this cylinder. So we just proved it. We're looking really good. A is 1/2, M is M, R squared is good. Looking over here. Once again, density is mass over, in this case, length, because this is linear mass density, and the length of it is 2L. So now I'm going to put in 2mL cubed over 2L times 3. I'm just putting this in for rho. You can see a bunch of things cancel out. An L and a 2, I'm left with 1/3 mL squared. Fantastic. The 1/3 is my A, the M, and L squared. This is the this is moment of inertia of a rod of length 2L. This one, oh wait, there's nothing to put in, but it has to be something M squared. So what I'm going to do is I'm going to go back to my original function. I said dm is 3x dr, and then I said dm is really 3x dx. I'm going to solve m in terms of x or L and put it back in. Let's integrate both sides from 0 to L. Integral of dm, this becomes m. The integral of this becomes x squared over 2. And I'm looking from 0 to L. So now I have mass is 3L squared over 2. So looking at this, I could then separate this out and say, oh, this is really kind of like 3L squared over 2 times 2, right? Same thing. And suddenly, this right here is an M. So I can simply say this is mL squared over 2. And that is moment of inertia. The A is 1/2 mL squared. This is how we look at different situations. And this is how we use calculus to figure it out. Write down your notebook, try it out, come with questions.